All right, so on today's agenda, we are first going to talk about effective values of periodic signals. After we talk about that for a bit, we are going to introduce the concept of complex power. So on the screen right now, I have a picture of what's referred to in the industry as a NEMA 515, I believe. Let me double check that. Yeah, I'm trying to remember if it's 515 or 15.5, but I think it's a 515. Anyway, anema 515 receptacle like we may find in our homes. This is probably the most commonly used receptacle in North America, or at least in the United States. The ones in your house may not have this rectangular form factor. They might be kind of an oval shaped, but hopefully every one of you can probably look around somewhere from where you're sitting right now and see a receptacle that looks something like this. Okay. So in this particular receptacle, where we see three prongs, the bottommost prong is our ground line. And if you have an outlet that doesn't have this bottommost thing like that, then it means it's an ungrounded outlet. I'm going to do this one in gray. It's typically actually attached to a white wire inside your walls. But this guy over here is what's called the neutral wire. And then over the right hand side, we have what's commonly referred to as a hot wire. And just for what it's worth, because some of your outlets in your home, the size of the place where you would plug in something on the neutral wire side and the hot wire side might be the same size. So that typically means that the polarity of the voltage applied across whatever you're plugging in doesn't matter. So if you can plug something in both ways, the polarity doesn't matter. But if like one of the legs on the plug is larger than the other, then the polarity explicitly matters. Anyway, just information for you all. So my question to you guys starting out here is, what voltage is supplied by one of these receptacles here in the United States?
Is it 12?
It is not 12.
120?
120, okay? So 120. Joey, do you
Yes.
know if electricity is distributed in the United States as a DC signal or an AC signal?
I think it's three-phase AC.
It is indeed AC, and it is typically three-phase over long distances. Not until we get into neighborhoods and stuff like that are we getting single phase. So you're absolutely correct there. So this is a question to kind of anybody, but what does 120 volts, which is what we commonly refer to as the voltage that's being supplied by one of these receptacles, what does that mean in the context of an AC system like we have in our homes and is used for transmitting and distributing electricity?
That means it shares the same phase angle with the current, correct?
So phase angle, same phase angle with the current just means that we're dealing with the resistance, really. That doesn't have anything necessarily to do with this. All right, so the question that I just posed to you guys. I genuinely didn't expect you to be able to answer. I was expecting a particular wrong answer, but that's okay. So we typically call the voltage drop across this thing 120 volts. That looks like a terrible 120, so let me fix that really quickly. What is left off of this description very regularly are three small but very important letters. And those letters are RMS. Okay. RMS stands for root mean squared. We're going to talk about that here in a moment. But realistically, what that RMS voltage is a representation of a time varying voltage signal, right? So if we were to connect an oscilloscope, which is a tool used to measure varying signals so that we can see what they look like as a function of time, the waveform that we would be looking at would be something like 169.706 cosine 120 pi t plus some generic phase angle theta v that really depends on when we start measuring things. So what, and this would be in volts. So what we're going to figure out here for the first part of this class is how the heck we wound up representing 169.706 cosine 120 pi t plus an arbitrary phase angle voltage as 120 volts, okay? 120 volts RMS is what's known as the effective value for this particular waveform, okay? So an effective value for a signal is a DC representation of the signal that delivers the same average power as the periodic AC signal. So if we were to connect a resistor across the terminals of this receptacle, it would absorb the exact same amount of average power as if we had connected a 120 volt DC source to that same resistor, okay? So that's all an effective value is. It's just a DC representation that delivers the exact same amount of average power as our AC signal does on average, okay? So we can come up with a mathematical relationship to go back and forth between our periodic signal and its effective value. So let's start by thinking about what the average power absorbed by a resistor might look like in a DC circuit, right? So in a DC circuit, the average power is literally just the power. It doesn't change, so the average value is the only value that we have. So we could represent that as the DC voltage squared divided by the resistance value, or we could represent that as the DC current squared times the resistance value. And these are relationships that you guys have been using since the third meeting of this class, and you probably wound up using them back in your engineering 120 series and all of that kind of good stuff as well, right? On the AC side of things, we know that the average power is going to be 1 over the period multiplied by the integral over 1 period of our instantaneous power. And this is what we talked about at the end of our last lecture. Well, we could represent the instantaneous power absorbed by a resistor as a function of its voltage waveform or its current waveform. So as a function of voltage, this would look like our instantaneous voltage squared divided by our resistance, and we're performing that integral with respect to time. Or it would look like 1 over t times the integral from 0 to t of our instantaneous current squared times the resistor value, and then we're integrating that with respect to time. So these two representations right here are just instantaneous power in terms of voltage and in terms of current. And then we are integrating the instantaneous power over 1 period, dividing by the period length, which gives us our average power, as was previously discussed. So if I set these average power relationships equal to each other, so like the DC average power and the AC average power, and I were to solve for the DC voltage or the DC current, that would tell me effectively what my effective value is. Because if the average powers are equal, we know that the effective value of a signal represents a DC representation that delivers the same average power, and that's how we're going to effectively sort that out. So let's look at the voltage relationships really quickly. So we have VDC squared over R. Well, the first thing that I'm going to do is I'm just going to get rid of that DC thing. I'm going to call this effective, because that's really what we're looking for when we do the algebra and all that kind of stuff here. So the effective voltage squared divided by the resistance, which is just average power in a DC circuit, is going to be equal to 1 over t times the integral from 0 to t of our periodic voltage waveform squared divided by the resistor value with respect to time. Now, we can see that there is a common factor of 1 over the resistance value on both sides of the equal sign here. So as it turns out, the value of the resistance literally does not matter at all, right? So I can get rid of it over here as long as I get rid of it over here as well. And so now, in order to figure out what our effective value is in terms of our periodic AC waveform, we simply need to just take the square root of both sides. And in doing so, we're given the relationship, the effective value of our voltage will be equal to the square root of 1 over t times the integral from 0 to t of the square of our periodic voltage waveform. So let's go back to those 3 little letters, RMS. RMS stands for root mean square, and what that is telling us is actually the mathematical operations that we are performing to get the effective value. So we are taking the square root of the arithmetic mean, also known as the average, of the square of our signal. So RMS literally tells us what to do to our periodic voltage waveform in order to get our effective value. If we did a similar derivation for the current relationships, so we can do that really quickly here, we would see that we would have IDC squared times R is equal to 1 over T times the integral from 0 to T of our periodic current squared times R with respect to time. Once again, the resistor values cancel out. I'm going to erase that DC thing and call this I effective. And taking the square root of both sides leaves us with the effective value of our current is simply the square root of 1 over T times the integral from 0 to T of the square of our periodic current waveform. So it's literally the exact same math. So this process of taking the root of the arithmetic mean of the square is how we're going to find the effective value of any signal that we're interested in. For us, it's always going to happen to be voltage and current, but in your later classes involving signals and systems, for those of you that are in electrical engineering, biomedical engineering, and things like that, this relationship will crop up again several times. Okay, so let's take a look at how to apply this particular equation. Okay, and the most important thing that we need to be looking for is that our signal of interest is periodic, because if it isn't periodic, its average value will actually be 0. Because if it doesn't repeat itself, we treat its period as it is infinitely long. Okay? And dividing by infinity is going to give us a 0 average value. All right, so let's say that I have the following signal. Just for the sake of argument, let's make it a voltage signal. And let's say that our voltage signal linearly increases from 0 volts up to, let's call this 8 volts for 3 seconds. And then it stays at 8 volts for 2 seconds. And then that cycle repeats itself once we hit 6 seconds. So we have this signal repeating itself over and over and over again. So as a piecewise function, I could say that my voltage waveform is going to have 3 distinct parts, right? It's going to have one functional value over the interval from 0 seconds is less than T is less than 3 seconds. It's going to have some other value over the interval from 3 seconds is less than T is less than 5 seconds. And it's going to have some third value over the interval from 5 seconds is less than T is less than 6 seconds before this repeats. So I'm just trying to describe exactly what's happening over one period. Okay? So let's start with the easy things. What is the value of the voltage over the interval from 5 seconds to 6 seconds?
Zero.
Zero. So it's just literally 0 volts. What about from 3 seconds to 5 seconds?
8 volts.
8 volts, absolutely right. And now for the slightly hard part, what is the value of the voltage over the interval from 0 seconds to 3 seconds?
12.
So it's not constant because we can see that it's changing as a function of time, right? It starts
Oh,
at
right.
0
It's not-
volts and increases up to 8 volts. Since it's a linear increase, we can literally expect this to just be in our good old y equals to mx plus b format, where m is the slope and b is the y-intercept. So what's the slope of this line?
Just 8/3.
Yeah, 8/3 measured in volts per second. Times time measured in seconds. And then what's our y-intercept?
0.
0. So I'm just going to leave the rest of that off. So are we okay with this mathematical description of the signal that I've drawn for one period? I'm going to take your silence as you agree that that is correct. So if we want to find the effective value of this thing, we need to, using the equation from before, effectively divide by our period, integrate over one period, and the signal that we are integrating is the square of our voltage, right? So what is the period of this signal?
Six seconds.
6 seconds. So it repeats itself every 6 seconds. Thank you, Joey. So that means that we're going to have 1 over 6 seconds. Oh, and I need to square root this whole thing. Sorry about that. One over 6 seconds times the integral from, so because we have a signal that is broken up into different parts over different intervals, we're going to break our integral up to match those intervals, right? So over the interval from 0 to 3 seconds, we are going to be integrating 8/3 volts per second multiplied by time, quantity squared with respect to time. Then we are going to be integrating over the interval from 3 seconds to 5 seconds, 8 volts squared with respect to time. And then lastly, over the interval from 5 seconds to 6 seconds, we're going to be integrating 0 volts squared with respect to time. So that in total, we have wound up integrating this signal over its entire period. Now, it is very obvious, or at least I hope it is very obvious, that the integral of 0 squared is just 0. So realistically, we don't need to include the intervals where our signal is 0, but I just wanted to do that for thoroughness' sake to make sure that we were integrating over the entire period of the signal. Okay. So we know that that last bit is just going to be equal to 0, which is why I've crossed it out. We're not going to worry about that part anymore. So looking at the other stuff that we have, we've got square root of 1 over 6 seconds times the integral from 0 to 3 seconds. So 8/3 volts per second squared to me seems like 64 over 9 volts squared per second squared times t squared dt. That's literally just me squaring our voltage signal for that interval. And then we're going to have plus the integral from 3 seconds to 5 seconds of 64 volts squared dt. Anybody have any questions about my math yet? Oh, and I should close this bracket. All right, so let's continue just hashing this out. So square root of 1/6 seconds. So what is actually, we can pull that 64/9 out. So what is the integral of t cubed?
T to the third divided by 3.
Exactly right. So t cubed over 3. But actually, so it's t cubed over 3, but now let's put the limits on that, right? So that's going to look like 3 seconds cubed over 3 minus 0 seconds cubed over 3. And then we're going to have 64 volts squared times the integral of dt. Well, what's the integral of dt? It's just t. So over here, we're going to have 5 seconds minus 3 seconds. Make sure I'm closing these brackets off correctly. So a good thing that we could do right here to make sure that we've done our integration correctly and all of that kind of good stuff is to take a quick look at what our units are going to look like, right? So in the numerator, we have a volt squared times seconds cubed. And down here in the denominator, we have seconds squared multiplied by seconds is seconds cubed. So we're going to have volt squared times seconds cubed over seconds cubed is just going to look like volt squared. So things are looking pretty good over here. Looking at our right-hand term, we have volts squared here. Seconds are coming from this, and then we have seconds in the denominator from that first term. So we're still just going to have a term that has units of volts squared. So everything seems to look like it's going to come out okay. So now we just need to sort through this stuff, which I'm going to be lazy and just use my calculator for, right? So I have the square root of 1/6 multiplied by 64/9 times 3 cubed over 3 plus 64 times 5 minus 3. And I wound up getting 5.657 and some change volts RMS. And I'm using the units of volts RMS to remind myself that we have just determined an effective value for this voltage waveform. So let's think about things in context here. Does this answer make sense? Okay. So if we look at our signal, its minimum value is 0 and its maximum value is 8. Okay, so our effective value should then definitely be somewhere between 0 and 8, which our answer gave us. So that's pretty good. We can see that for a large portion of its duration, it's over that 5.6 thing, right? So like over this interval from a little less than 2 all the way out to 5, it's above that. And then for this interval from here to the left, it's below that. So that seems like a reasonable estimation for the effective value for this signal. So that's just kind of a sanity check type thing. There's not any real teeth to doing that method. It's just, if we found the effective value of this signal and it said something like 17 volts, well, we'd know, hey, there's no way in hell that's remotely possible because our signal is never even around 17. So anyway, all right. So that is an example of determining the effective value of just some made up garbage signal, okay? Now let's talk a little bit more about effective values for signals that we see commonly in electrical engineering, okay? So let's say that I have a current signal this time. Doesn't remotely matter because the process is the same. And the signal that I am interested in behaves in this particular way, okay? So let's say that it is some value, let's call it V naught, for half its period, and then it cycles down to negative V naught for the other half of its period, and just repeats itself over and over and over again. So this is typically what we would call a square wave. Where this value right here corresponds to t over 2, and this value of time right here corresponds to t. Then we would have 3t over 2, 2t, and so on and so forth. So if we wanted to find the effective value of this signal, we could define I of t as a piecewise function, just like we did earlier, where we're going to have two intervals. One from 0 is less than lowercase t is less than capital T over 2. And then the second interval is from capital T over 2 is less than lowercase t is less than capital T. So what is the value of our signal over the interval from 0 to capital T over 2?
Is it just 0?
It is
V
not
naught.
0. V naught. And what is the value of our signal over the interval from capital T over 2 to capital T? So effectively
Negative.
this bit right here.
Negative V naught.
Negative V naught, absolutely right. Okay. So putting this into our effective value relationship, we could say that I effective is going to be the square root of, well, our period is literally just t in this case because we're doing things generically, times the square root from 0 to capital T over 2 of V naught squared dt plus the integral from capital T over to capital T of negative V naught squared dt, like so. So looking at our next step in our math here, that's going to look like 1 over capital T times the integral from 0 to capital T over 2 of V naught squared dt plus the integral from capital T over 2 to capital T of V naught squared dt. We can pull out that common factor of V naught squared, so that we'll have 1 over T times V naught squared. Actually, let me pull that all the way out. So let's put that V naught squared over here. The integral from 0 to capital T over 2 of dt plus the integral from capital T over 2 to capital T of dt. What is the value of this thing that I've underlined?
I want to say it would just be 0, wouldn't it?
It would not. So
T over,
so if we look at this first bit here, right? So the integral of dt is just t, right? And then we would substitute in the bounds of our integral. So that's going to look like t over 2 minus 0 plus, and then we have the exact same thing here. So we're going to have capital T minus capital T over 2. So this positive capital T over 2 cancels this negative capital T over 2, and it is literally just capital T. So we have effectively capital T in the numerator and capital T in the denominator, which means our effective value for this thing is literally just V naught. So for a square wave in which exactly half of the time our signal is high, so at V naught, and exactly half of the time our signal is negative V naught, the effective value is the same as if we just had the voltage either positive all the time or effectively negative all the time. So that's a kind of interesting thing. We can treat a square wave pretty much as if it were just a DC signal having one of the two possible polarities. Let's look at a series of rectangular pulses. Okay. So arbitrarily, this one is just going to be a voltage waveform. Give me just a moment. Somebody's spam calling me. I figure it might be a doctor or something. I don't know who it was. They hung up as soon as I answered. All right, sorry about that. So let's say that we have a voltage signal. And this time, let's have our voltage be V naught yet again. And then it's going to drop down to 0. I'm going to call this point in time X times capital T. And then over here, this will be capital T. Like so. So we just have a rectangular pulse that's on for some fraction of its total period, where that fraction is what's called the duty cycle. That's a number between 0 and 100%, where a 100% duty cycle literally means a DC signal. This part right here would be T plus XT, and this repeats over and over and over again. So you could think of this as a part of a pulse width modulated signal, because the width of the pulse isn't modulating, it's just constant. But this is what, you know, like if we wanted our servos to run at a constant speed or something like that, this is actually the type of signal that we're feeding the control line on our servo. So as a piecewise function, our voltage waveform looks like V naught over the interval from 0 is less than lowercase t is less than x times capital T. And it looks like 0 volts for the interval x times capital T is less than t is less than capital T. So if we have a series of rectangular pulses like this, our effective value for our voltage waveform would be the square root of 1 over capital T times the integral from 0 to x of t v naught squared dt plus the integral from xt to capital T of 0 volts squared dt. Obviously, this second bit right here just goes to 0 because the integral of a constant value of 0 is just 0. And so we're just left with this part over here on the left-hand side. So that's giving us the square root of 1 over capital T. I'm going to pull out that constant factor of V naught squared. And so we're just integrating dt over the limits from x of t minus 0. So that our effective value is then simply V naught times the square root of x. So the effective value of a series of rectangular pulses is highly dependent on whatever the duty cycle is for those rectangular pulses, which absolutely makes sense. The longer that our signal stays high, the larger our effective value should be. All right. We could do triangular waves, but I feel we're 45 minutes in. So let's circle back around to a sinusoidal signal, which is what we're really interested in at this point in the class. Okay. So let's say that I have a current waveform. I am cosine omega t plus some phase angle theta I. I want to know what its effective value is. Okay. So the first thing that I want to sort out is what's the period of this signal? for what it's worth, this is something that we discussed on our class meeting where we reviewed sinusoids and all of that kind of good stuff, right? So in that particular class meeting, we learned that omega is equal to 2 pi times the linear frequency. And we also know that the linear frequency f is the inverse of our period. So that's going to look like 2 pi over t. So rearranging this guy, our period is then 2 pi over omega. So when we apply our equation for an effective value, we are going to have the square root of 1 over t. So that's going to look like omega over 2 pi times the integral from 0 to 2 pi over omega of I of t squared dt. Now I'm simply going to substitute in I squared. So that's going to look like 1/2 Im squared plus 1/2 Im squared cosine twice omega t plus twice theta I. I did that using the exact same trig identity I used at the beginning of class on Monday. Not expecting you guys to remember it or anything like that, but I'm just explaining that's how I got this result. So we could split this up into two integrals, kind of like we did yesterday talking about our formal definition for average power, where we would have omega over 2 pi times the integral from 0 to 2 pi over omega 1/2 Im squared dt. That 2 looks like hot garbage. And then we'd also have an omega over 2 pi times the integral from 0 to 2 pi over omega of this 1/2 Im squared cosine twice omega t plus twice theta I dt. So I'm going to draw a picture here that'll kind of help us sort out what's going on with that second integral there. So this is t. Let's say that this signal in blue represents I of t. Over exactly one interval, right? So this length right here, or over one period. So this length right here would be t. Okay? Well, if I were to plot this AC portion here, its magnitude is going to be 1/2 of Im squared. So Im squared would be up here, multiply it by 1/2, and we're back down here. So this same point, but our signal is oscillating at twice the frequency. So it should come down here, go back up, like so. So what is the area under the red curve from 0 to capital T. All right, so let's, sorry, go ahead.
Would it be this? I'm probably way off base. Would it be the same amount of area as the blue?
So you are actually correct, but I don't think you're correct for the right reasons.
I'm thinking it's because it's double the frequency, but it's half the period length.
So, all right, so let's look at this thing. And again, perhaps you guys' issue is with the fact that I can't draw a sinusoid to save my damn life, okay? So let's look at some things really quickly here. So I have this area right here that represents 1/4 of a cycle of a sinusoidal signal. And then I have this area right here that represents 1/4 of a cycle of a sinusoidal signal. What would happen if I added those two areas together? Notice that one is above the horizontal axis and one is below the horizontal axis.
You would get the same area as that area of the blue sinusoidal above the horizontal axis.
I would not. I'd get 0 because I have some amount of positive area and some amount of negative area, and they're the exact same area. Right? So it's effectively the same thing as I have this amount of area above the axis and this amount of area below the axis. When I add them together, it's 0, right?
Makes sense.
Okay. So all we're doing effectively with our integral here is we are integrating this sinusoidal signal over exactly 2 periods of the double frequency signal, okay? Anytime that we integrate a sinusoid over an integer number of periods, the answer will always, always, always be 0. Because for any sinusoid, exactly half of the time the signal is above the horizontal axis, and exactly half of the time the signal is below the horizontal axis, and the signal is symmetrical about the horizontal axis. So anytime we're integrating over an integer number of periods, the area above the curve exactly cancels out the area below the curve. So that convoluted explanation is why we get to say this whole thing goes to 0, because we are integrating that AC double frequency part over exactly 2 periods of that sinusoid. So all we're left with is this bit over here on the left-hand side, which is all constants, which makes our life way, way easier, okay? So moving our constant terms over, we have omega over 2 pi times 1/2 the magnitude of our current squared times the integral from 0 to 2 pi over omega of dt. Well, the integral of dt over the interval from 0 to 2 pi over omega is literally just equal to 2 pi over omega. So this integral is the reciprocal of this thing over here, so they cancel each other out. And all we're left with is the magnitude of our sinusoid divided by the square root of 2. So this is a pretty interesting revelation for a couple of reasons, okay? Our effective value here is independent of frequency, meaning the value of omega literally does not matter at all. If our signal is oscillating at 1 hertz or 1 megahertz, the effective value is just the magnitude of the signal divided by the square root of 2. This result is also independent of phase angle, right? There's no relationship with theta I left inside of this thing at all. So why this is so interesting / important is that different countries within, North America, Europe, Asia, and all of that kind of stuff, we distribute power at different angular frequencies or different linear frequencies, which happens to also mean different angular frequencies, right? So here in the United States, we use 60 hertz for our power distribution networks. In Europe, they use 50 hertz. In Japan, I believe it's north of a particular river, they use 60 hertz, and south of that same river is 50 hertz, and it's just because of which countries occupied Japan after World War II and helped rebuild their infrastructure after we nuked them and all of that kind of stuff. But anyway, so it doesn't matter where you are in the world, the effective value of a sinusoid is always the same thing. So that makes designing using these effective values a very convenient method to check all of our power relationships without having to get bogged down in the details of, well, we're doing this in the US, so it needs to be this way. We're designing this thing for a European market, so it needs to be that way. None of that matters because the effective value of a sinusoid is always just the magnitude over the square root of 2. All right. So before we introduce the concept of complex power, let's look at in-class assignment number 23, problem 1. Okay. So in this particular problem, we are asked to determine the average value of our signal first, and then the effective value of our signal. Actually, sorry, before we do this, let me backtrack and do one other thing. Okay. So this result, I'm going to put it in a box here because it is very important to understand, and this is true for voltage signals as well, is what happens when we have a sinusoidal signal of exactly one frequency. But we could have a sinusoidal signal containing multiple frequencies. So what if we had something like V of t is equal to 8 cosine 5t plus 10 cosine 10t plus 5 cosine 15t, and so on and so forth. Just for an example of where somebody might see a signal like this, would actually be on power lines here in the United States. So the electricity that we consume and use to power all of our equipment and all of that kind of good stuff, like toasters, microwaves, and all that jazz, that is sent out at a 60 hertz frequency, so an angular frequency of 120 pi radians per second. But they also superimpose on top of that very, very high frequency signals, sinusoidally oscillating signals. And they do some traveling wave analysis, and that's how they figure out where faults are and all of that kind of good stuff, to let service workers know like where effectively a power outage and all of that kind of stuff began. So if you ever wondered, you know, how does a guy in a bucket truck know where the line is broken to go fix it? It's because they send that high frequency signal for testing purposes on top of the low frequency power signal. But anyway, so this is definitely real world applicable stuff. So if we wanted the effective value of this signal, we could use our generic equation, but it gets really, really gross really quickly because we have all of these multi-frequency terms. Well, as it turns out, there is a simple method for determining the effective value of a signal that just contains multiple sinusoids. And it works as follows. The effective value is going to be the square root of the effective value at frequency 1 squared plus the effective value of frequency 2, sorry, that should be a subscript, squared plus the effective value of frequency 3 squared, and so on and so forth. So for the numerical example I gave you guys above, that would be as simple as, all right, so this is definitely a sinusoid, so its effective value is 8 over the square root of 2, square it. Now we have our next frequency term. It's a sinusoid. Magnitude over the square root of 2, square it. The third term, we have a magnitude of 5 divided by square root of 2, square it, and we would just continue doing that for any higher order terms that we would have. It is literally that simple. If we had a DC term, so let's say plus 10 volts. We could do the same thing. What's the effective value of a DC signal? Or what do you guys think the effective value of a DC signal would be?
Whatever that signal is.
Exactly right. Because by definition, the effective value is a DC representation of the signal. So the DC signal itself is the effective value. So we would literally just add the DC voltage to that. I'm bringing this up because you guys have a homework problem or two related to it, and we can actually use this relationship for in-class assignment number 23, problem 1A, to make our life way easier for stuff. So that's what reminded me to tell you about it. Sorry about being maybe more scatterbrained than normal, or maybe it's a regular amount of scatterbrained, who knows. All right, so circling back around to our in-class assignment problem. Let's look at part A here, which is, in my opinion, the significantly harder of the two problems, okay? Determining the average value. Anybody have any thoughts on the average value for signal A, the one on top?
Two volts.
2 volts, exactly right, because half of the time the signal is above 2 and half of the time the signal is below 2. Does not need to be any more difficult than that. It's a sinusoid. oscillating around a DC value of 2 volts. So its average value is 2 volts. 100% agree. So VA average is 2 volts. Great job. For the effective value, we could, if we were so inclined, do the, square root of 1 over t times the integral, all of that kind of good stuff, or we can use the relationship that we just figured out, okay? So I personally would describe the signal VA of t as 2 plus, so we have a DC offset, so that's why I'm saying it's 2 plus, and then I have this AC signal on top, right? What's the amplitude of just the AC portion?
Would it just be 1?
Yeah, so let's just call this 2 plus sine omega t volts. Since we're looking for an effective value, we know that omega doesn't matter. So that's why I'm not bothering to figure out what it is, okay? So the effective value of this thing, so VA effective, should just be the square root of, actually, I made a mistake here, that should be 10 squared. 1 squared plus, oh, sorry, that's not right. 2 squared plus 1 over the square root of 2 quantity squared. And if we put that in our calculator, so let's see, square root of 4 plus 1/2. 2.121 volts RMS. Literally, the correct answer, I should have updated this to put RMS there, but anyway. That is a much, much easier way to do that problem than the way that you are technically intended to do it.
Dr. Hartman.
Yes.
Oh, why would the amplitude be 1 on that signal?
So, what's the distance from the positive peak to the horizontal axis effectively?
Just 1.
That's why we put 1 there.
Okay, gotcha. Just didn't know if there was a calculation we were supposed to do or if we were just supposed to eye it.
Nope, literally just eye it. I will say that on the exam or something like that, I'll make sure that the graph is set up in such a way that like its amplitude is exactly 1 or exactly 2 or something like that, because this one, it looks like the peak value is halfway between 2 and 4, but I can make MATLAB's grid make that more obvious, and I try to do that on the exams, just for what it's worth. All right, so any questions about part A here? All right, so now let's look at part B. So I know that the answer was literally right there, but eyeballing this thing, what do you think the average value of VB is?
$7.5 volts.
Yeah, because half the time it's 5 and half the time it's 10. So on average, it's 7.5. Now for us to calculate the effective value of this thing, we're going to need to use our relationship, right? So V effective B would be equal to the square root of, so what's the period of this signal?
From 0 to 4, so 1 over
So
4.
4 milliseconds, okay? So we're going to have 1 over 4 milliseconds. There are 2 intervals, so I'm going to split my integral up into 2 intervals. So my first interval is going to be from 0 to 2 milliseconds. What is the value of our signal over the interval from 0 to 2 milliseconds?
5
All
volts.
right, so 5 volts squared dt plus the integral from 2 milliseconds to 4 milliseconds. What is the value of our waveform over the interval from 2 milliseconds to 4 milliseconds?
10 volts squared
10
dt.
volts. Thank you, Haley. There we go. And we're now at a point where we could literally just throw this in our calculator and it's going to wind up coming out to 7.906 volts RMS. So I have not yet put up your practice tests and all of that kind of good stuff, but I intend to do that this afternoon. This level of difficulty, so like the example problem that I worked here in particular, and then those 2 in-class assignment problems, that's kind of the level of what you should expect for an effective value problem on your test. And other than the gross multi-frequency sinusoid ones, that's roughly the level of difficulty that you're going to see on your homeworks and stuff like that as well. So this topic, I hope you guys feel, isn't particularly difficult, but it is a big stepping stone / building block of the last thing that we're going to be talking about in this class, which we're going to spend the next 2 class meetings on, complex power. So with that in mind, let's get into complex power. Okay, so in Monday's class meeting, we learned that for a network, a linear black box network that is sinusoidally excited, where the voltage drop across the terminals of the network will be V of t, and the current flowing into the terminals of the network will be I of t. And let's just say specifically here, V of t is Vm cosine omega t plus some phase angle theta v. And I of t is equal to Im cosine omega t plus theta I. We learned that the average power absorbed by this network was given by 1/2 Vm Im cosine theta v minus theta I. So I'm going to take that average power relationship and I'm going to play around with it a little bit here. Okay? So we could say that P average is equal to, so I'm going to take that factor of 1/2 and I'm going to split it up between my voltage magnitude and my current magnitude. So I could write that as Vm over the square root of 2 times Im over the square root of 2 times the cosine of theta v minus theta I. Right? Well, what is Vm over the square root of 2 for a sinusoidal signal? What does that represent?
It just represents our value.
What kind of value? I'm looking for a specific word that we literally talked about a whole bunch 5 minutes ago.
Root mean square.
So VM over the square root of 2 is the root mean square of our AC signal, also known as the effective value, right? So this is nothing more than V effective times I effective cosine theta V minus theta I. So using effective values means we got to get rid of that pesky 1/2 sign for DC relationships. Okay, so that's one added bonus of this. Now, this might be a little bit of a leap for you guys, but you actually have the background for this. What does this thing right here represent? Well, what it represents is the real part of the following operation. Okay, so if I multiplied V effective with a phase angle of theta V by I effective with a phase angle of theta I conjugate, that is literally this thing right here. So we typically call this thing V with a tilde over it. And this thing right here will be I conjugate with a tilde over it. So let me explain what that tilde notation means. Okay. So earlier in this class, we learned that for a time domain signal, V of t is equal to Vm cosine omega t plus theta v. And for a time domain current, Im cosine omega t plus theta I. We could represent those signals in the frequency domain by using phasors, where our phasor voltage V is just Vm with a phase angle of theta V, and our phasor current I is just Im with a phase angle of theta I. Okay. So over here, we have time domain, signals, and right here, we have our frequency domain signals that we've been dealing with for the last several class meetings. We're going to take those frequency domain signals one step further, and we are going to enter the RMS phasor domain. And the RMS phasor domain is where all power calculations occur. Okay. So our RMS phasor voltage, that's V with a tilde over it, is literally nothing more than our phasor voltage V divided by a factor of the square root of 2. So that would be Vm angle theta V all divided by root 2, which is the same as Vm over root 2 with an angle of theta V, or simply V effective with an angle of theta V. So it's the exact same thing as our frequency domain phasor, except that we're not using the magnitude of the voltage anymore. We're using the effective value of the voltage. That's literally the only difference, okay? Effectively, we invented this fancy math and this new domain to get rid of having to deal with that damn factor of 1/2 that cropping up into all of our calculations. That is literally the point of this. Doing the same thing for the current, we would have phasor current I over root 2, or Im angle theta I over root 2, which is just Im over root 2 angle theta I, or I effective angle theta I. And this, as I said a moment ago, is what we call the RMS phasor domain signal. Okay, so this operation, RMS phasor voltage V times the complex conjugate of RMS phasor current I, sorry, I don't know why that popped up, is what's commonly called in power engineering complex power. Okay, so S with a bar over it, and I'm going to put a note here. Complex power is equal to RMS phasor voltage V times the complex conjugate of RMS phasor current I. Okay, so realistically, this is the only equation that you need for complex power calculations. What we are going to do for the rest of today's class is kind of unpack this relationship and talk about the different parts of complex power. Introduce a few things that help us understand what's going on. And then at the beginning of our next class meeting, we are going to play around with the relationships that we developed today in order to be able to express things only in terms of voltage, only in terms of current, all that kind of good stuff to make our calculations easier. But realistically, all of the power stuff that I'm going to ask you guys to do on your last exam can be done using literally this simple equation. Multiply the RMS phasor voltage times the conjugate of the RMS phasor current, and then know what the different parts of complex power are. Okay. So here is where things get weird / confusing, because the math, I hope, is incredibly simple. It's literally multiplying two numbers together. What do you guys think the units of complex power should be?
Is it
Watts?
ohms?
So I heard somebody say watts. That answer makes sense, but it is technically wrong. So let's talk about why it makes sense. RMS phasor voltage V is a voltage. RMS phasor current I is a current. So every other time we've multiplied a voltage times a current, we've come up with a power measured in watts. But all of those powers that we've calculated to this point have not been with complex numbers, okay? So electrical engineers effectively invented a unit for complex power that helps us to differentiate complex power from the average power that we've been calculating up to this point. So the units of complex power is the volt ampere, commonly expressed as simply VA. So that is the unit of complex power. It is identical to a watt in every way, but we use volt amperes to refer to complex power and to differentiate it from average power. Okay, so that's why it has this special unit. All right, so Our complex power S is, by definition, the product of two complex numbers, which means it is also a complex number. And since it is a complex number, it could be represented in either rectangular form or polar form. And each part of those rectangular representations and polar form representations has a special name. Okay, so we're going to talk about that here. So in rectangular form, if I multiplied V, RMS phasor voltage V times RMS phasor current I conjugate, I would get V effective times I effective cosine theta V minus theta I plus J V effective I effective sine theta V minus theta I. Okay. So this real part right here is our average power. And average power is measured in watts, as it has always been in this class. Okay. Let's talk about what this represents. So the average power absorbed by a system is effectively the portion of the complex power that is capable of performing mechanical work or capable of being converted into heat. Okay, so it is the portion of the complex power that is incapable of being stored. All right, so average power is associated with the resistance in a system or network. Okay, the imaginary part over here is what is commonly referred to as reactive power. And reactive power also has made up units to help us distinguish it from average power and complex power. So reactive power is measured in volt amperes. Excuse me, I misspelled that. Reactive, commonly referred to as VARs. Okay. So reactive power is the portion of the complex power that can't be converted into heat. Okay, so it represents the energy storage, particularly the temporary energy storage in our systems. Okay, so it is associated with capacitances and inductances, or the reactances in our system. I believe I mentioned a couple of days ago when somebody had asked a question about brownouts and all of that kind of stuff, or when like you see your lights dim in your home or something like that. Like that typically happens when there's not enough reactive power in the system to help the grid as a whole ride out some sort of fluctuation. Okay, so that's the kind of thing that you might see. So like there's a famous example of it in Great Britain after a World Cup game where I think England had been eliminated. Everybody effectively turned on their electric tea kettles at the same time, and that caused such a large drop of average power that the city of London experienced a blackout because there was not enough reactive power in the system to ride that out. A similar thing, I believe, happened in New Orleans when Beyonce played the Super Bowl. Effectively, right around the halftime show with all of the fancy electronics and this, that, or the other, the Superdome lost its power and wasn't able to be brought back on until they added a static VAR capacitance into the power feed to help them be able to bring the power back up. So even though the reactive power is imaginary because it's got a J in front of it, it is critical, absolutely critical to the health and stability of our utility grid. Okay, so all right. So let's throw some symbols on these things. So average power is symbolized by P, and then we may typically put a little AVG under it to remind us that it's average power. But our average power is the real part of complex power. And then reactive power is typically given a symbol Q, so that in rectangular form, our complex power can simply be expressed as P plus JQ. So any questions on this before I move to the polar form quantities? Actually, I want to make a comment here. Okay. So I hit you with this equation and this equation. I genuinely do not expect you to ever use those two equations. They are 100% correct, but I don't expect you to use them. So let me explain why. Let's say, we'll do a quick example here. We have an RMS phasor voltage across an element of interest is 12 angle 15 degrees volts RMS, and an RMS phasor current of 2 angle 35 degrees amps RMS. I want you guys to calculate the complex power. Literally just use this equation up here and tell me what answer you get. Not trying to be any ruder than I usually am, but I'm a bit confused as to what is taking so long.
24 angle 50.
Okay, so you've made an error because you did not take the conjugate of I.
That's what I was waiting for you to tell. I figured I did it wrong. I was just forgetting what that star was.
Yeah, so
I
that
got-
starts with complex conjugate operation. What did you get, Haley, I think?
I got 24 angle negative 20.
So 24 angle negative 20. Okay, so 24 angle negative 20 degrees volt amperes. Okay, convert that into rectangular form for me, please.
I got 22.55 minus 8.21.
Okay. What's the average power?
The 22.55,
Yeah, great. What's the reactive power?
the negative 8.21.
Great. Did you have to use those bullshit equations that I put above? Absolutely not, right? So if you can do this simple calculation correctly, you never have to do those other ones because your calculator, when you tell it to give you the answer in rectangular form, literally gives you average power and reactive power, as long as you remember that the average power is the real part and the reactive power is the imaginary part. So those equations above are kind of pointless. Okay. So that's the what I'm trying to illustrate with. It's very easy to get overwhelmed in this portion of the class because I'm hitting you with equation after equation after equation. But realistically, as long as you can do this one, you're good for literally 99.99% of things. Okay. So don't get super freaked out about all of the information because it literally all boils down to that one relationship. Okay. All right. So I'm going to move this example problem down the page a smidge. I'm going to talk about the polar part of our what do I do to find the conjugate? So you can have your calculator do the conjugate operation for you. That being said, the conjugate of a complex number, all that means is you change the sign on the imaginary part for rectangular form complex numbers, or change the sign on the angle for polar form complex numbers. So the calculation that I was expecting you guys to do was effectively 12 angle 15 degrees volts RMS times 2 angle negative 35 degrees amps RMS, because 2 angle negative 35 degrees is the complex conjugate of 2 angle positive 35 degrees. David, did that answer your question? No problem. All right. So circling back around, we have, let's say, some understanding of the rectangular form here. Now we're going to talk about the polar form, right? So in polar form, this operation would give us V effective times I effective with an angle of theta V minus theta I. Okay. V effective multiplied by I effective is what is commonly referred to as the apparent power. An apparent power, because it is nothing more than the magnitude of the complex power, is also expressed in volt amperes. Okay. So you can think of apparent power as kind of a worst case scenario for a power system. And what I mean by that is it ignores any difference in phase. So that is effectively the largest amount of power that you would see. The average power will always be less than or equal to the apparent power, and the reactive power will always be less than or equal to the apparent power, because the apparent power is the magnitude. So if we have a system where all we have is average power, then the average power and the apparent power are equal. When we have a system where all we have is reactive power, then the reactive power and the apparent power are equal. And any other situation the average power and the reactive power will be less than the apparent power. So apparent power is what is used to design systems, power systems effectively. In fact, I don't know how many, if any of you guys have ever tried to buy an uninterruptible power supply for your computer or anything like that, or maybe size a generator for your house or help your parents size a generator for their house. But typically speaking, those types of power equipment typically have two ratings. One is average power in watts, and the other one is apparent power in volt amperes. So if you tried to buy an uninterruptible power supply or a UPS for your computer, it might say that it's rated for 1800 watts, 1800 watts and 2100 volt amperes. That's effectively telling you, hey, if you use this to power your computer, it could only power a small fan or something like that on top of that, because any other type of induction motor thing would cause it to draw too much reactive power and would make the thing fail. So anyway, apparent power is used in the design of power systems all the time. The National Electronics Code uses apparent power for practically everything. The symbol for apparent power is just effectively the magnitude of our complex power S, because that is literally all it is. So going back to that example, which of these four numbers here is the apparent power?
Four.
The 24. Yeah, so 24 volt amperes is the apparent power, 22.55 watts is the average power, negative 8.21 volt amperes is the reactive power, right? So once again, you really don't even need to know the equation. As long as you understand that it is the magnitude of the complex power, you're good to go. And then lastly over here, we have what is commonly referred to as the power factor angle. This is an angle just measured in degrees, and its symbol is typically theta S. I actually talked a little bit more than I had intended to for today, so I'm going to cover one last thing really quickly, but I didn't get quite as far as I wanted to. So for the in-class assignment here, don't worry about problems 2 and 3. We'll knock those out on Friday. Okay. All right, so the last thing that I want to talk about for today is what's called the power triangle. And the power triangle is nothing more than a graphical representation of the relationships that we literally just learned, right? So some type of load, let's put it like this. So this is my real axis, this is my imaginary axis. If my load is absorbing some amount of complex power S, like so, the projection of S onto the real axis is the average power. The projection of S onto the imaginary axis is the reactive power. And the angle formed between the positive real axis and S is our power factor angle. And lastly, the length of this vector is our apparent power. So this is just graphically representing the fact that S, which is equal to RMS phasor voltage times the complex conjugate of the RMS phasor current, can be expressed as P plus JQ in rectangular form, or the magnitude of S angle, power factor angle, in polar form. So if you can remember this picture, it literally tells you the real part is average power, the imaginary part is reactive power, the magnitude is apparent power, and the angle is the power factor angle. So it's just all of the relationships that we talked about in a compact visual form. All right, any questions before we get out of here for today? All right, well, I'm almost positive that I did overwhelm you all, but I hope I didn't. If you think of any questions, we're going to continue talking about complex power and all of that kind of good stuff on Friday for sure. So if you have any questions, you can either save them for Friday, or you can shoot me an email and I will try to compile your questions and answer them all in our next lecture. I hope you guys have a great rest of your afternoon, and I will see you on Friday.